Questions 8 through 10 on the 2008 Grade 12 Euclid Math Contest. Points A, B, C, and D are arranged as shown with AB parallel to DC. And P, the point of intersection of AC and BD. Also, angle ACB is 90 degrees. AC is equal to CB and AB is equal to BD, which equals 2. Determine the measure of angle DBC. Let's start labeling this diagram and doing so with the information given in the question stem. AB is equal to BD is equal to 2, so that means that's 2, and they've already labeled that. And BD is 2, so from there to there is also 2, so I'll just put a 2 there. Hopefully this will not get too messy. AC is equal to CB, okay, so that means this is equal to that. So that is an isosceles triangle, so we'll just write that. Those symbols to indicate those two are the same. ACB is 90, okay, they've already labeled that. Anything else? AB is parallel to DC, so this line is parallel to that line. Okay, I think that is all we are given, so let's begin with this question. The first thing I'm going to do is I'd like to figure out the length of these sides, and that can be done pretty easily with Pythagoras. So CB squared plus AC squared is equal to AB squared, since that is a right triangle. And then AB we know is 2, and then CB is equal to AC, so I can just write CB squared plus CB squared, like that, and that's 4. So 2CB squared is equal to 4, and therefore CB squared is equal to 2. CB therefore is root 2. So that takes care of that. Now, the next part, of course, involves a little bit of, interpretation. The first thing I'm going to do is I'm going to connect D to A, like that. Okay? And then I want you to look at two triangles. The first one is this one right here, ABC. And the next one is this one right here, ABD. Those two triangles have the same area. Now, why do they have the same area? Well, because they share the same base, which is right here, and they also have the same height. If you draw a line from C to AB, it will be the same length as D down to AB. Why? Because this sentence right there, AB is parallel to DC. So the heights will be the same. So for example, if I draw a height from D down to AB, that's make it perpendicular, right? And similarly, if I draw a height from C down to the bottom, that distance will be the same. Those two triangles have the same area. So since they have the same area, we can write them in an equation. Area of ABC is equal to area of ABD. And I will label this height as H, right there, like that. So here we go. Area of ABC is pretty easy because we can just do this as the base and this as the height, right? Since that's a right triangle. So it's 1/2 base, which is AC, times height, which I can write as BC, like that. And then ABD, this triangle, that one is going to be 1/2 base, which is AB, times height, which is H. And then all of these, we know the numerical value. First and foremost, the halves cancel. AC, I just figured out, was root 2. And then BC is root 2. CB, BC, same thing. And then over here, AB, well, that's given as 2, and then that just leaves me with H. So this allows me to solve for H. This side becomes 2, 2H, and therefore H is equal to 1. So there we go. So I'll just write that in there. H is equal to 1. All right, so now we have to start talking about what they want in the question, which is determine the measure of angle DBC. DBC is this angle right here, so I'll just write theta to indicate that. Okay, well, this triangle is isosceles, right? So that means this angle and this angle are the same. And we'll just call that y, I guess. Have I labeled anything else y? I don't think so. So we're safe by calling that y. And that's 90. So that basically means that 2y plus 90 is equal to 180. And therefore 2y is equal to 90. So y is 45 degrees, that angle. So if y is 45 degrees from here to here, and this is theta, then this angle is y, which is 45, minus theta. Okay, so we're almost done. I think I can squeeze it in to the same page. Now the final step is to look at this triangle right here. This one that goes from D to B and then meets the height. If you look at that triangle, that has a right angle right here. So I can use trigonometry, and in particular I will use sine. The sine of this angle right here, the sine of 45 minus theta. And sine, as you know, is opposite over hypotenuse. So in that triangle, the opposite is h, and the hypotenuse is dB. So I've got the sine of 45 minus theta over h, which I just figured out was 1, and dB. What is dB? Well, go back to the question. They tell you dB. dB, or BD, is equal to 2. Right? That had to be used somewhere. So there you go, 1 over 2. So that means that 45 minus theta, in terms of degrees, if you do the inverse sine, is 30 degrees. So therefore theta is 15 degrees. And there you go. That is what they wanted in the question, that theta right there. In the diagram, ABC is a right angled triangle with P and R on AB. Also, Q is on AC and PQ is parallel to BC. If RP is equal to 2, BR is 3 and BC is 4, the area of triangle QRC is 5, determine the length of AP. They want that length right there. Let's start with a little bit of labeling. I will let my AP, which is what I have to find, equal x. So I'll just write x right there. And then not too much additional labeling is required. QP is the only other one. I'll call that h. So this guy is going to be h right here, Q to P. Okay, so what we have to do in this question is figure out x, and we can do that by looking at the area. So the full area, and then that will equal individual areas added together. So the full area is that big triangle, and that is 1/2 base times height. The base is all the way from there to there, so that's 3 plus 2 plus x, so that's 5 plus x. And then the height is from there to there, which is just 4. So that part's pretty straightforward. And then that equals the sum of all these triangles. So this triangle, that triangle, and these two guys, right? So there's 4 triangles there. So the first one is pretty straightforward. That's right there. It's just 1/2 base times height, which is 1/2 3 times 4. The next one is here. Well, that one, the good news is they tell you. That's QRC, and they tell you the area is 5. So that's very helpful. And then the next one would be this guy right here, this small one, QRP. So that's going to be 1/2 base, which is 2 times height, which I have called h. And the last one is the smallest one, APQ, which is 1/2 base, which is x, times height, which I have called h. And there you go. Now, unfortunately, we have 2 variables. If we only had one, then we'd be done, meaning we could solve it. But we have 2 variables. We have h and we have x. If we can get h in terms of x, then we can substitute and solve. The good news is that can be easily done. How? Through similar triangles. There's two triangles that are similar, and those two are this guy, which is APQ, and the full triangle, which is ABC. So I think I can do that up here. Triangle APQ is similar to the big triangle, which is ABC. So that means the ratio of the sides is the same. So h over x in the small triangle is equivalent to 4 over 5 plus x, which is the base of the large triangle. So this is my relationship. I can isolate for h. Here we get 4x is equal to h times 5 plus x. And therefore h is equal to 4x over 5 plus x. So that will allow us to solve now. So let's try to simplify this as best as we can. This is now just straight algebra. So we got 2 times 5 plus x, and this is going to be 12 divided by 2, which is 6, and that's just a lone 5. This becomes just h, and that becomes x over 2, and then for h, I'll just leave it as h for now. And then now we can substitute for our value for h. So this becomes 10 plus 2x. This is 11. And then now I've got 4x over 5 plus h. And then I've got x over 2 times 4x over 5 plus h. So I can bring this over. This will be 2x minus 1. And then I can add the fraction here if I multiply top and bottom by 2. This will be 8x plus 4x squared all over 2 times 5 plus x, like that. All right, so far so good. Cross multiply and you get 2x minus 1 is equal to 2 times 5 plus x. Let's see, factor out of 2, and we will get 4x plus 2x squared. The 2's will cancel, and all you will be left with, if you expand this, is 10x plus 2x squared minus 5 minus x, and on this side it will be just 4x plus 2x squared. The 2x squareds will cancel, and you are left with, on the left side, 9x minus 5, and on the right side 4x. If you bring the 4x over, it becomes 5x is equal to 5, and therefore x is equal to 1. The equation 2 to the power of x plus 2 times 5 to the power of 6 minus x is equal to 10 to the power of x squared has two real solutions. Determine these two solutions. We have 2 to the power of x plus 2 and 5 to the power of 6 minus x, and that is equal to 10 to the power of x squared. And we obviously have to get some sort of a value that makes us do a log at the end, because I'm pretty sure this involves logs. And the fact that they gave us a 10 here and 2 and a 5 here makes me think that I have to combine them, because 2 times 5 is equal to 10. But I can only do that is if the exponents are the same, and right now the exponents are not the same. Okay, so I have to somehow get the exponents to be the same. And I think I can do that. Let me just do a little bit of algebra here. This guy right here, which is 6 minus x, if I take something away or add something, regardless, right, then I can make it look like x plus 2. So if I, for example, add something, let's just say it's k, I can make it look like x plus 2. So that means k would be x plus 2 minus 6 plus x. So that looks like 2x minus 4. Okay, so that makes sense. If k is 2x minus 4, and then I add it, then I can make it look the same. So that essentially means that x plus 2 minus k is equal to 6 minus x, like that. So instead of 6 minus x, I will put x plus 2 minus k. So I get 2x plus 2 times 5 to the 6 minus x, but I'm going to put x plus 2 minus k like that. And this allows me to combine. So this now becomes 2x plus 2, 5x plus 2 times all over. Well, I can just leave it as 5 minus k for now, and then I can put it downstairs later. The important thing is that these two exponents are now the same, and I can combine them. So 2 times 5 is 10, so it becomes 10 to the x plus 2. 5 to the minus k is 10 to the x squared. Okay, so far so good. I hope you're following. It's not that difficult of a technique. All right, so now, what do we do now? Okay, well, let's put this all on one side. Put the 10s on one side, so we get 10x over 2, x plus 2 all over 10 to the x squared. And then this can go on the other side as 5k, like that. Okay, at this point is where we can start combining and things will start happening for us. 10 to the x plus 2 minus x squared is equal to 5 to the power of k. Correct? Now we can introduce logs. So I need some space here. So when I take the log of both sides, that's what it will look like. And of course, log rules state that you can put this in front. So it becomes x plus 2 minus x squared. And we got the log of 10. And I didn't put a base. And when you don't put a base, it implies it's base 10. And similarly, the k can come out front. And we got the log of 5. All right, log of 10 is just equal to 1, correct? So that just disappears. So you just have x plus 2 minus x squared. And this is going to be log of 5, which is a number. So that's good. We don't have any more variables. And then we put the k down here. Now k, remember, is equal to 2x minus 4. So I've got everything now in terms of one variable. So I got x plus 2 minus x squared over 2x minus 4. All right. So now at this point, we've got to do a big, long equation involving a quadratic. So here we go. We've got x plus 2 minus x squared is equal to 2x minus 4 times the log of 5. Right, the log of 5 is some number. I'll just keep it as log of 5 for now. Put everything on one side and isolate. We got x squared. If you expand this, you'll get plus 2 log 5x minus x minus 2 and then minus 4 log of 5, like that. Okay, I think we're all done here. I just have to collect like terms and then I can use a quadratic. So the x coefficient is going to be 2 log 5 minus 1, and then the end there is minus 2 minus 4 log of 5. All right, not pretty, but we can use this to figure out x. Quadratic. X is equal to minus b, so that just is going to be 1 minus 2 log 5. I can just reverse it. It's perfectly allowable. And then, oh boy. So I've got 2 log of 5 minus 1 squared minus 4ac, and c is minus 2 minus 4 log of 5. All over 2. Okay. So this is where you get out your calculator, and without making any mistakes, you try to figure this whole thing out. And if you do, you get, I'll let you do that, you get the following decimals: minus 3979 plus or minus 4.3979 square, no, that's after you take the square root and all divided by 2. And if you do this, you get 2 and minus 2.379. Oops, 3979. Yeah, So these are the two solutions. Now, my question is, and I sincerely hope the answer is yes, is this acceptable? Because this is actually, in terms of like logs, it's the log of 250, or the negative log of 250. You can check on your calculator. So I hope that they accept it in this format, because these are indeed the two solutions to the original equation. And you can go back and verify, and I encourage you to do that, that if you do have these two values, does it actually satisfy this original equation, which is right here? And that shouldn't take too long, so I'll let you guys do that. Determine all real solutions to the system of equations x plus log x is y minus 1, y plus the log of y minus 1 is z minus 1, and z plus the log of z minus 2 is equal to x plus 2, and prove that there are no more solutions. So the approach to this question involves the following. We try to make this as simple as possible. And you do that with some substitutions. The first is you let a is equal to x, and then b equal to this y minus 1, and c equal to z minus 2, like that. If you do, the equations become as follows. A plus the log of a is equal to b. When I don't write a base, it's assumed as base 10. So that's why I'm not writing in base 10. And then the next one becomes b plus 1 plus the log of b is equal to c plus 1. And you can remove the 1 from both sides, so it just becomes b plus the log of b is equal to c. So I got this, and you got this. And then the third one becomes c plus 2 plus the log of c is equal to a plus 2. So that means c plus the log of c is equal to a. So there you go. Now, these three equations are obviously a little bit cleaner, and we can work with this. The first step is actually surprisingly simple. You just use observation. You can notice that if a equals 1, then b would equal 1, right? For example, in the first equation, we've got 1 plus the log of 1, right? If I let a equal to 1, and that is 1 plus 0, since it's log of 1 to the base 10, and that is equal to 1, and that equals b. So b is 1. And then similarly for c, if b is 1, c also equals 1. And you can verify that by plugging 1 as the value of b into that equation. So my very first solution is a equals 1, b equals 1, and c equals 1. Okay? So that's very straightforward. But remember, we have to follow the variables in the question. We introduced, or I introduced ABC. X, Y, Z are a little bit different, right? If a is 1, that means x is going to be 1. If b is 1, y will be 2. And if c is 1, z will be 3. So x, y, z is actually 1, 2, and 3, like that. So this is a solution to that equation. Okay? So now we have to get into this part, which is prove that there are no more solutions, or find all real solutions. Okay, so here we go with the next step. What we have to do is look at what a can be. We already proved that it could be 1, right? But what about, can it be less than 0? Less than 0, between 0 and 1, and finally greater than 1. These are the only sort of possibilities, right? We can look at each one. Well, the first one we already did. How about less than 0? That is not possible because you're taking the log of a, and you can't take the log of a negative number. So that's out. Now we will look at these two. Can it be between 0 and 1, and can it be greater than 1? And if the answer is yes, we'll find what are the actual values of a. If the answer is no, then it's not possible. So first let's start with 0 is less than a is less than 1. Okay, so in general, if that is true, then if we look at the first equation, which is a plus the log of a is equal to b, a is some number, right? It's between 0 and 1, so it's some small positive number, 0.5, 0.7, whatever. But if you take the log of a number that is less than 1, it results in a negative number. Okay, try it. Take your calculator out, take any number between 0 and 1, take the log of it. You get a negative number. So that means that b is less than a. Okay? Because you're taking a and subtracting something from it. So b is less than a. Okay? So that's very important to understand. In a very similar way, if we look at the next equation, which is b plus log b plus c, we've got b plus log b is equal to c. b is less than a. Well, a itself is less than 1, so b has to be less than 1, right? So b is also some small number between 0 and 1. So if I have just b, that's going to be a positive number. But again, if I take the log of b, it's going to be some negative number for the exact same reason. So that means that c is less than b. Correct? So now let's move on to our third equation. And that tells me that c plus log c is equal to a. Well, again, if c is less than b, then it's also less than 1. It's in this range, so it's some fraction, 0, or some small number. So that's going to be a positive number because it's greater than 0. But if you take the log of any number that's between 0 and 1, it results in a negative value. And therefore, a is going to be equal to less than c. Same reasoning. Now, if you combine all of these guys, you get a is less than c, c is less than b, and b is less than a. Okay? A is less than c, c is less than b, b is less than a. Well, that makes no sense, right? That's contradictory. So, since that is a contradiction, it means that this cannot hold true. So, put a little X there. Okay? So, I hope that makes sense. I hope that wasn't too difficult to understand. And if you're, having a problem with this, my advice is just to choose a number. Instead of, this kind of stuff, just choose like a equals, 0.7, and then go through the same thing that I went through. It might be a little bit clearer. Now we're down to the last one is, can a be greater than 1? If it is, we'll try to find what values of a that help us solve this system of equations. Okay, here we go. If a is greater than 1, so that means the first one, which is a plus the log of a, is equal to b. That means we've got obviously a positive number plus a positive number, right? If a is greater than 1, then if you take the log of it, it'll be a positive number. And that is equal to b. So that basically means that b must be greater than a, right? Because you're taking a and you're adding a positive number. So b has to be greater than a. All right? So very same thing for b. B plus log of b is equal to c. And since a is greater than 1 and b is greater than a, b is also greater than 1. So again, you have some positive number. If you take the log of a number that's greater than 1, it'll be positive, and that is equal to c. So that means c is greater than b. Okay? And in a very similar way, the c plus log of c is equal to a. Exact same scenario. Positive number is equal to a. So a must be greater than c. And then combining, you get a is greater than c, which is greater than b, which is greater than a, which is again a contradictory inequality. And because it's a contradiction, that means a greater than 1 cannot be true. So we have eliminated everything. The only one that worked was when a is equal to 1. So therefore, the solution to this question is only the one we figured out just by observation, which is right here. X, Y, Z is 1, 2, 3, which I got from A, B, and C all being equal to 1. Suppose that n is a positive integer. Consider an upward pointing equilateral triangle of side length n cut up into unit triangles as shown, n equals 3, n equals 4. For each n, let f at n represent the total number of downward pointing equilateral triangles of all sizes. For example, f at 3 is equal to 3, f at 4 is equal to 6 plus 1, which is 7, as illustrated below. Determine the values of f at 5 and f at 6. So this is an interesting question. The first thing, of course, is to understand what it is that they're talking about, and then we'll try to find f at 5 and f at 6. So here's an equilateral triangle, and it's upward pointing, which is self-explanatory. And then what they say is they want you to count the number of downward pointing equilateral triangles of all sizes. And they help us out, which is good, by giving us two small examples. The first is when n is 3. So that means that you've got 3 small unit triangles. That's what that means, n equals 3. And that's how they make the big triangle. And then the downward pointing you can just count, because this is a fairly small number. For n equals 4, it's pretty much the same thing. You can count the small guys, and those are illustrated. But then there's one big one too that you have to add, because they want downward pointing equilateral triangles of all sizes. So you can't just count the small ones. You have to figure out, are there any bigger ones as well? And they did, and they found that you've got one bigger one. So that's why it's 6 plus 1, which is 7. So we have to figure out manually f at 5 and f at 6. So here we go. First, let's draw a triangle that has 5 unit triangles at the bottom. Here we have the triangles, and we can figure out f at 5 and f at 6. So f at 5, first and foremost, the unit ones that are fairly straightforward: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the ones that are units, that's 10. And then we have to see if there's any additional ones that are a little bit bigger. And that would mean triangles that have a base that is 2. So there's one, and there's another one, and there's another one right there. So 3 of those guys. So that means 10 plus 3, which is 13, is the value for f at 5, which we are figuring out manually. Now let's turn our attention to this triangle and try to figure out f at 6. Well, again, 1, 2, and so on, 3, all of these guys. And that's pretty straightforward. You just count those. And if you do, that will total 15. And then, as before, we have to figure out, are there any more that are bigger in size? Okay, first let's just look at the ones that are 2 by 2. And remember, it's downward pointing. So we got 1 there, 2 there, 3 there, 4, 5, and 6. So plus 6. Now, are there any more that are bigger? That would mean a 3 by 3. And there's one of those right there in the very middle. So there you go. We got another one. So in total, 15 plus 6 plus 1 is 22. So f at 5 is 13 and f at 6 is 22. So that takes care of part A. Part B, prove that f at 2k is equal to f at 2k minus 1 plus k squared for each positive integer k is greater than or equal to 1. Now, to do this question, part B, we have to actually figure out a general formula for f at n, or f at k, So let's discuss how we can figure this out. Now, what I'm going to do is, first and foremost, I'm going to list the values for all the f at n values from 1 up until 6. And staring at this, I was able to figure out a pattern. You notice how it goes 1, 3, 6, 10. Some of you will figure out what this pattern is. And then similarly, when you look at the other numbers, which would be the larger downward pointing triangles, it's again 1, 3, 6. And then if I do that, you'll see it also starts off 1, 3. And I'm pretty sure that if you keep doing this, f at 8, f at 9, the pattern becomes very obvious. And that pattern is as follows. F at n, when n is just equal to either 1, 2, or 3, right? We have to talk about this sort of case by case because it's not always going to be the same. When n is just 1, 2, or 3, it's fairly straightforward. It's just n minus 1 times n all over 2. Now, you say, well, how on earth would you be able to figure that out? It's actually not that complicated. It's just the sum. Well, watch, let me show you. This triangle you've already seen, right? 1, 2, and then the next row you got 3. The next row you got 4. The next row you have 5, right? You're just adding up consecutive numbers. 1, 2, 3, 4, 5. So if I were to say, how many of these little guys do you have? It's 1 plus 2 plus 3 plus 4 plus 5. And that, of course, is equal to 15. Correct? And this is like 1 plus 2 plus 3 all up until n in this case was 1, 2, 3, 4, 5, 6. So all up until n minus 1. And I'm sure by grade 12 you know that the sum of consecutive integers has a formula. If you have 1 plus 2 plus 3 all the way up until n, the formula is n times n plus 1 over 2. But in this case, we're not going to n, we're going to n minus 1. So if you're going to n minus 1, it'll be n minus 1 times n minus 1 plus 1 over 2, which is n minus 1 times n over 2. So that's how I got this guy right there. Okay? Well, that takes care of n equals 1, 2, and 3. But what about if n is bigger? What about if it's 4 or 5? Okay, that's not going to be as straightforward. We still keep this guy, right? But then, if you notice, once it's 4 or 5, we've got another add-on here. You see, notice that? We've got another set of triangles, and those are the bigger triangles. So for example, this is when n is 6, right? So there was the 2 by 2s that we had to add, right? These guys, 1, 2, 3, 4, 5, 6. And in a very similar way, there's 1 here, 2 here, and 3 here. Exactly the same pattern, but this time it's not for n, it's for n minus something. And that is n minus 3. So in addition to this guy, you have to add n minus 3 times n minus 2 times all over 2. So remember, it was 1 plus 2 plus 3, right? Those 2 by 2s. And how did I get that? Well, in this case, n is 6, this triangle. So we got that by going 1 plus 2 all the way up until n minus 3. And then, of course, you use that famous formula to get the addition, and that's how we got this formula right here. Okay? So I hope that makes sense, and I'm not going to go through this every single time, but by this point, you understand. So that takes care of 4 and 5. I'm just going to do a couple more, 6 and 7, and then 8 and 9, and then we'll try to put this all into one formula. For 6 and 7, it's the same thing, n minus 1. We keep those guys the same. And you also keep the next one, n minus 3, n minus 2, all over 2. But then we have to add one more. Like, notice here, we've got to add another one. So we go right back to the same thing, and it's going to be n minus 5 times n minus 4 all over 2. All right? And then I'll just do one last one, which is when n is equal to 8 or 9. It's pretty much the same thing. But this time you're going to add n minus 7 times n minus 6 all over 2. Okay? And this just keeps on going and going and going. So our job is to figure out all of this in one equation. Well, this is sort of our pattern, but we have to sum it all into one. And that is our task, and in all honesty, that is a difficult task. This, what I did, is actually not too bad. Most of you, I'm sure, understood how I did that. But we have to combine this, because this keeps on going, right? Dot, dot, dot. When n is 10, 11, it'll be another 1, and then so on. So how do we combine them into one equation? And we do that as follows. We first split it up into two categories. The first is when n is an even number of the form 2k. And the other category, of course, is when n is odd of the form 2k minus 1. And for each of these, we have to figure out how to combine all of those together. So the first one, we have f at 2k is going to be obviously a summation of some sort. And this is the part of the question that is quite challenging, in my opinion, trying to combine these. And with a little bit of manipulation of numbers and trying to figure out how this will work, you come to the following conclusion that it's 2k on both sides. So that starts off kind of very similar to what we have up here. But then the next part is very tricky, and that is 1 minus 2m, we have to introduce a variable, plus 2 minus 2m. And it's a summation, so it's going from m equals 1 all the way up until k. Now, that I know is quite challenging, and you think, well, how on earth did you come up with that? Well, let's look at an example. Let's say 2k is equal to 8. Okay? And the reason I chose 8 is because this formula up here was for n equals, if you remember, equals 8 or 9. Just until this point. It ends right there, actually, when n is equal to 8 or 9. So, if we just look at that and look at n equals 8, what do we get for this equation up here? Plugging in values into this one, we would get the following. We get 7 times 8 plus 5 times 6 plus 3 times 4 plus 1 times 2. And of course each of these is over 2. And this is what we get when we plug in 8 into this equation that I had figured out earlier. Now we want to see what we get for this equation using our same value of 8 for 2k, and therefore k is going to be equal to 4. So when m is 1, you get 7 times 8 over 2. When m is 2, remember we're going from 1 to k, so we're going from 1 to 4. It's going to be 5 times 6 over 2. I'm just substituting into this formula right here. When m is 3, it is going to be 3 times 4 all over 2. And then when m is 4, 2k is 8 throughout. It's 1 times 2 over 4 over 2. So as you can see, both systems produce the same result. To move forward with this, we have to make a substitution that allows us to work with this a little bit easier. And that substitution is we let p equal k plus 1 minus m. And if we do that, this will help us solve this to get it all into one equation, because we can't have a summation. We have to somehow combine it. So this now becomes m equals from 1 to k. 2p minus 1 times 2p all over 2. And then that 2 can cancel out this 2, and then we just have to multiply through by p. And if we do that, we get 2p squared minus p all in brackets, and that is from m equals 1 to k. All right. Continuing, here we have to break this up into the summation of m equals 1 to k of p squared, and then minus that is the summation of 1 to k for p. Now, you know that this guy is p times p plus 1 all over 2, right? That's just the sum of the consecutive integers from 1 until k. But because it's k, we have to put k here. So just make sure. It doesn't really matter. I mean, the letters are not important, but just to be consistent with the question. All right? But this one here, how do you do that one? That is the sum of not consecutive integers, but consecutive perfect squares. Some students may not know that one. That is as follows. That formula is 2k plus 1 times k plus 1. So it's similar, but obviously it's not the same formula. All over 6. This right here. And then, of course, don't forget about the 2 in the very beginning. Okay, now we have to simplify this. Factor out a k times k plus 1. And then in brackets, you will have 1/3 2k plus 1 minus a half, like that. And then combining, this becomes k times k plus 1, 2/3 k minus 1 over 6. And therefore, this all becomes k times k plus 1 times 4k minus 1 all over 6. And that is our formula for f at 2k. Now we go back to the very beginning because we have to do this whole thing all over again, but this time for 2k minus 1. So we have to now do f at 2k minus 1, and that is going to be very similar. We have to combine all of these that are up here into one equation. So it starts off with 2k on both sides, but then this is where the question becomes difficult. We have to figure out how to do that. And it's minus 2m on that side. Here it's plus 1 minus 2m. And the summation this time is going from 1 to k minus 1. All right, we proceed. So just like before, we have to make a substitution to allow us to figure this out a little bit cleaner. And that substitution is going to be let p equal k minus m. And then we can proceed. F at 2k minus 1 becomes the summation from m equals 1 to k minus 1. And this cleans up pretty quickly. It becomes 1/2 2p times 2p plus 1. And then we can just get rid of the 2's here and then multiply through by p. And if you do, you get 2p squared plus p. And that, of course, is the summation of m equals 1 to k minus 1. And then this, of course, just like before, we break it up. P squared plus the summation of p. And this one here, that one you know, but just be careful because we're going up to k minus 1 now. So it's k minus 1 times k all over 2. And then this one, it's the same formula, but just be careful because we're going only to k minus 1. So that becomes k minus 1 times k times 2k minus 1. And that's all over 6. And don't forget about that 2 right there. So I'll just simplify it. I mean, we're simplifying in a very similar way that we did over here, where you factor out a k minus 1 and a k like that. And then in brackets, you're going to have 2k minus 1 over 3 plus a half. And in the end, it will be k minus 1 times k times 2k over 3 plus a sixth. And at the very end, we get f at 2k minus 1 is equal to k minus 1 times k times 4k plus 1 all over 6. So there we go. We got two equations. Now, at this point, we have to go back and remind ourselves what is the question asking us. We had to spend all that time trying to figure out the equations. We have to show this, that f at 2k is equal to f at 2k minus 1 plus k squared. Well, the good news is that we got both formulas, so we can probably easily prove that. We have to prove that f at 2k is equal to f at 2k minus 1 plus k squared. All right? We can rearrange this and write f at 2k minus f at 2k minus 1 is equal to k squared. And the good news is that f at 2k we have a formula for, and f at 2k minus 1 we have a formula for. So let's put that in. Let's just concentrate on the left side. So that's going to be k times k plus 1 times 4k minus 1 all over 6 minus k minus 1 times k times 4k plus 1 all over 6. All right. So let's proceed with this. Can anything factor? I think so. 1 k and a 6 on the denominator. And all we're left with here is k plus 1, 4k minus 1, and then minus k minus 1 times 4k plus 1. And this is k over 6. I guess we have to expand this, so this becomes 4k squared minus k plus 4k minus 1, and then minus 4k squared minus k plus 4k plus 1. All right, collect like terms. Let's see here. These go, the ones go. So I'm just left with 4k, which is 8k minus k, so that's 6k. And this is just k squared. And there we go. We just proved it. So that completes 10b. Determine with justification all positive integers n for which f at n is divisible by n. As before, we have to look at this from two standpoints. The first is when we have f at 2k, and that means basically that n is a even number. And then the second scenario is when we have f at 2k minus 1. So that basically means that n is odd. And for each of these, we have a formula. For f at 2k, we know that is equal to, as we figured out before, k times k plus 1 times 4k minus 1 all over 6. And f at 2k minus 1, we figured out earlier, was k times k minus 1, 4k plus 1 all over 6. All right? But we are not interested in 2k, all that stuff. We want f at n. So for each of these, we have to put a value of n. So for the first one, we have to let n equal to 2k. So that means we will have f at n, and then put that in there. This gives me that n over 2 is equal to k. So wherever there's a k here, we've got to put n over 2. So I have n over 2 plus 1 times 4 times n over 2 minus 1, all over 6. And simplifying, this whole thing, you will get n times n plus 2 times 2n minus 1 all over 24. And in a very similar way over on this side, again, we want just n, so we'll let n equal to 2k minus 1. And if you do that, you get n plus 1 over 2 is equal to k. So we want to substitute that for the value of k into this. So that becomes n plus 1 over 2 times n plus 1 over 2 minus 1 times 4 times n plus 1 over 2 plus 1. And that's all over 6. So f at n, if you simplify this whole thing, is going to be n plus 1 times n minus 1 times 2n plus 3 all over 24. Okay, so now we got formulas that look just like f at n, right? One for even and one for odd. We have to figure out all the values of n for which f at n is divisible by n. So what does that mean? F at n is divisible by n. Well, let's just start with this one. If f at n is divisible by n, it means that it gives some integer value, right? So for example, some integer, whatever you want to call it, p, let's say. Okay, so that means f at n is equal to np. And the same story here, right? F at n divided by n is going to be some integer, and therefore f at n is equal to np. So using that fact, we can try to figure out values for n. So first, let's concentrate on this one right here. I think that's going to be a little bit simpler. So if f at n is equal to np, I put that in here. np is equal to n plus 1 times n minus 1 times 2n plus 3 all over 24, like that. All right. So I can multiply, cross multiply, and if I do, I get 24np, and then expand this, n squared minus 1 times 2n plus 3, like that. And then keep expanding, and this will give me 2n to the power of 3 plus 3n squared minus 2n minus 3 is 24np. And then let's put the 3 on one side, and this just becomes 2n to the power of 3 plus 3n squared minus 2n minus 24np. And then you can factor out the n, and that just leaves you with n squared plus 3n minus 2 minus 24q. Okay, so that means this times this is equal to 3. So either it's a situation of 3 times 1, where n is equal to 3 and this whole thing is equal to 1, or it's a situation of 1 times 3, where n is equal to 1 and this whole thing is equal to 3. Regardless, we just figured out that n can be either 1 or 3. It's these guys right there. This value is not important to us. So there you go. I've got 2 values of n, 2 actual numerical values. Now let's turn our attention to this guy over here. So this means that np is equal to n times n plus 2 times 2n minus 1 all over 24, right? So 24 np is equal to n times n plus 2 times 2n minus 1. All right? Now, what we can do at this point is just get rid of one of those n's, so you're just left with 24p is equal to n plus 2 times 2n minus 1. So 24 times p is equal to n plus 2 times 2n minus 1. So that could mean that this is 24 and this is p. But one thing for sure is that this whole thing has to be a multiple of 24, right? Because it's 24 times p. So what I'm going to first do is set n plus 2 as my multiple of 24, 24k, some multiple of 24, that I know for sure. If that is the case, that means that n is equal to 24k minus 2. So any number that is of that form will be valid as a value of n for the conditions of our question, 24k minus 2. Let's do the same thing for this guy. Maybe that will work. 2n minus 1 is equal to 24k. If that is the case, we get 2n is equal to 24k plus 1, and therefore n is equal to 12k plus a half. And that half, unfortunately, doesn't help us because n has to be an integer. So that didn't work. So somehow we have to deal with this 2n minus 1 value in a different way. Okay, I think I can do that. We have 24p is equal to n plus 2 times 2n minus 1, right? Well, 24 is really 8 times 3. So this perhaps is going to be a multiple of 8. And if so, this has to be a multiple of 3, right? That's the only way you're going to get 24. So if that is the case, then I can let my n plus 2 equal to 8, some value, right? 8k or 8a, whatever. And then that means that n is equal to 8a minus 2. And then this guy I chose to be a factor of 3 because 2n minus 1 is an odd number, and that's why I chose that as the factor of 3. So that means 2n minus 1 is some like 3k, let's say. It's a multiple of 3. So now going back to my original equation and substituting, I've got 24p, but instead of n, I'm going to put this guy right here. So it's 8a here, right? Because I let that equal to n plus 2. And then 2n minus 1, instead of n, I'm going to put this, 8a minus 2. So I've got 8a minus 2 minus 1. And if you expand this, you get 8a, and you get 16a minus 5. And that is equal to 24p. So again, we've got an 8 here, and then we've got this expression. That expression must be a multiple of 3, because that's the only way you're going to get 34. So it's got to be some multiple of 3, 3k2 again. And that will work if you let a equal to 3, let's say k3 minus 1. If a is of that form, then this will hold true. So going back and looking at our value of n, remember n is right here, it's 8a minus 2, and we just will substitute this right here. So that would mean 8 3k minus 1 minus 2, so that becomes 24k minus 10. If n is of this form, this will also work for our condition that the question poses. So n is either 1 or 3, n is of the form 24k minus 2, or n is of the form 24k minus 10. And if it is, going back, let's just read the question. For those values of n, f at n will be divisible by n.